Hello there and welcome to our next video in the series of 1.2.4 of 1.2, if that makes sense. So this is the second part video of 1.2.4 and we are looking in this one at assembly language programming, and we're going to look at the little man computer notation that we're going to use. And if you've ever heard of that before, the LMC, have you ever seen that before? It can be really confusing, but the idea behind this is to explain how data moves through the fetch, decode, execute cycle and uses assembly language commands to do everything you need it to do. However, I'm not going to use this today because I'm going to show you how you would do it in an exam, which is what you're going to need coming up, hopefully. So here is a list of common assembly language instructions. So on the left hand side column there where it says instruction, we've got load, store, add, subtract, input, output, end. We've got branch if zero, branch if zero or positive, and branch always, and then we've got something called data storage. In the middle we've got the mnemonic, and that is the shortened version of the word. So LDA is load the address, load from the address, should I say. And you've got STA, store at the address. You've got add, which is addition, subtraction. IMP, input. Out is output. HLT is halt, or stop the program. We've got BRZ and branch if zero. BRP is branch if zero or positive. BRA is going to branch always. And then we've got data storage, so the mnemonic in the middle. And that's what we write. We write those mnemonics, and we'll be given those mnemonics in our exam in terms of you will see a question and it will have some assembly language in it, and you'll have to basically either dry run it and put some data in it, or you'd have to correct it, or you'd have to write your own. So in the third column, we've got something called machine code. Anywhere where you see an X, 5 is what you'd write down. You'd write the number 5 for a load command, and then you would provide the next two numbers, usually, which are the address. That's where it's stored. So 511 would be stored in memory address 11, for example. 3, again, where the X's are, would replace them with numbers. 1, replace them with numbers. 2, replace them with numbers. And then you get to input commands. And 901, because it's not expecting you to input an address, because you're not saving or retrieving, you're asking the user for something, you don't need any address from the user there. So we have 901 for input and 902 for output. 000, again, no address needed because we're ending. And we've also got branch if zero. Branch commands have addresses as well. Now in the bottom, the data storage there, think of data storage, dat, as our variables. So if you want to store a value in a memory address or a memory location, you would use dat to set that up originally. Okay, and you'll see that in the exam questions as we go forward. The last column explains what each mnemonic does. So if you see the letters LDA, we are loading the contents of the memory address provided and we're placing it into the accumulator. Store, STA, store the value currently stored in the accumulator in the memory address. Add the contents of the memory address provided to the accumulator. Subtract the contents of the memory address from the accumulator. Input and output, take the input if the address is 1, or copy the output if the address is 2. Stop is the end command or the HLT command. You've got branch, BRZ, branch to the memory address if the accumulator is 0. Then you've got BRP, branch to the memory address if the accumulator is 0 or positive, and then branch always, use the memory address as the address of the next instruction. So you're going to branch no matter what. They're like our if statements branches. Okay, and then finally you've got dat, which indicates a location that contains data. Let's put some of these in practice so you can see them in context, because that's going to be important. Here, I've got an example which is adding two numbers together. First one, we're going to start with an input because we need the input from the user, so we'll request it from them, and that's a 901 command, remember. Then you'll see STA first. Now, in the previous table, you can see there that the store command, let me just get my pen. The store command has sta and it's 3 and then XX for an address location. Now in here you can see that I've put sta first. Now first is my memory location. I've just give it letters instead of a number there. So sta first. So we store the input from the user in a location called first. The second one, we take a second input now from the user and store it in the accumulator, and then we add first to that. Okay, we're going to add first. So whatever's in the accumulator, we're going to add first to it. Then we output the result of the two numbers added together, and then we halt. Okay. Now, at this point, you're also going to need some data. So first, a variable that contains 0 currently. Now that's going to go over your head 100%. So what I'm going to do is I'm going to run this like I would as a student. So if I was you, I would use something called the boxing method here, and I would have a box, and I draw these in the exam on any bits of paper that you can get your hands on or the back of the exam paper. And I'm going to have a box for the accumulator, because I know I'm going to need that because all of these use the accumulator, and I've also got a data storage, a DAT called first. So I write in there first. In addition to that, I have another box, and this is my output, my out box there. Okay? So when you input something, let's say I inputted the number 5. Okay? It's going to say sta first. So store whatever's in the accumulator, which is 5, because I've just inputted it. So 5 goes into the accumulator. Store that value from the accumulator in the first variable box. So I store that in there. Then I take a second input from the user, 4. Now that overwrites what's in the accumulator, and we store 4 in there. Then it says add to the accumulator whatever is in the first variable box. So I go to first, I have a look, 5. I take 5 and I add it to whatever's in the accumulator, and that results in 9. And then it says out. So 9, whatever's on the accumulator, gets outputted to the user, and then we halt and we stop, and the program is done. And that's a very, very simple assembly language example there. So let's make it a little bit harder. So in this next example, we're going to find the bigger of two numbers, and when you ask students how you would even go about doing this using the predefined commands that we've got, just remember we can only store, we can load, we can add, subtract, and we can check if things are positive, and that's about it. So how are we going to do this? Well, what you would do is you would think about storing two numbers. We can input two numbers, no problem. So let's input 5, for example, and then let's input a second number at 10. And let's say we subtracted the second number from the first. You've got 5, you take 10 from that, and it leaves you with -5. Now that means if you've got a negative number, that means the second one was bigger. If you flip that around and said, well, what about the second number here subtracted from the first? Well, that would leave you with 5, wouldn't it? Which means that because you've got a positive number here, then that means the first number is still bigger. So that's the kind of concept that we're going to take towards this, the answer to this approach here. So we're going to input our first number. We're going to store it in a data store called first. We're going to input a second number, and we're going to store that one as well in a data store called second. Then we're going to make sure the second is actually loaded in the accumulator, which it should be, but we're belt and braces approach here. Then we're going to subtract the first number from the second that's sat in the accumulator, and we're going to store the result of that back in the accumulator again. After that, you're going to check to see what's left in the accumulator, and you're going to see if it's positive or 0. And if it is positive or 0 here, then you're going to jump to second is larger. Now that's called a label, and that allows us to jump between different lines of assembly language instructions, because assembly runs in sequence, one line after another. So let's see this happening then. So if the result of the accumulator is positive or it's 0, we will change and jump to second is larger and carry out the assembly language from there. However, if it's not, we move on to the next line. That next line would be load the first number and output it, and stop the program. Down here, this is the label. So second is larger is what we call a label. I'll try and draw that on my tablet. There you go. And that links to there. So if it is, if we branch, if positive or 0, if it's positive or 0 in the accumulator, we will jump down here and skip over these lines or these commands here, and then we'll hit this one, the label. Then we'll load second into the accumulator, so load the value that's in the second data store into the accumulator. We'll output that one, and we will halt the program. And don't forget, we have some data storage going on. We've got a variable called first and a variable called second. So let's actually see this in motion. And again, the reason why I use the box method is because it allows me to visualize it, and I'm not taxing my brain too much. As long as I can update these boxes and follow the steps line by line, you cannot go wrong, it seems, but people still do. Okay, but you're trying to take that cognitive pressure off yourself. I need an accumulator. I need a variable, a data store called first. I need a data store called second. I need a data store for outputs as well. So I have another one called out in there. Okay, so input, let's try this. Let's go input 5. So we put 5 in the accumulator. We store whatever's in the accumulator in the first data store. So we put that in. Then we input 10. Accumulator gets overwritten with the value of 10. That gets stored in second. So 10 goes in second. Then we load second. Load it. 10's already there. Happy days. We subtract first. Well, what's first? First is 5. So let's subtract that from 10. 5. We've got 10. We minus 5 from it. And that gives us 5 overall. Okay. Then we look inside the accumulator and see if it's a positive or 0. Is this a positive or 0? Yes, it is. Therefore, we jump to second is larger. So we go down here and it says LDA second. So we load second into the accumulator. There you go. 10 gets loaded in there. And then we output it. So we output 10. And then we halt and we stop and we're done. So we've outputted the largest number and we've found the biggest of two numbers. Let's try it the other way around, just to prove the point. Okay, we're going to input the first number being larger this time, so we'll go with 10. So here's my ACC. Here's first. Here's second. Can't spell. And here's out. Drawn very crudely. So we've inputted the first and we stored that. So we input 10, that goes into the accumulator. Store 10 in the first box. We input the second one, smaller number this time, which is 5. Okay, so 5 goes into the accumulator this time and it gets stored in second. Then we load second. Well, 5's already there, so happy days. And we subtract first. So we take 10 from 5 and that gives us minus 5. Then it says branch, if positive or 0, second is larger. Now this number here is not positive and it's not a 0. So no, we're not going to jump. We move to the very next line in our sequential order and then we LDA the first number. So LDA first, 10 gets loaded there. And then we output that. So we output the value of 10. So no matter what, we're always going to find the biggest of two numbers. So what does this look like in an exam? We've got an exam question here. The following assembly code is written for the Little Man computer instruction set. We've got input, store, load, loop, sub, arg. So we've got to look at this. This is the exam context we've got. It says state the output when the inputs are 13 followed by 5. Okay? Now on the right hand side, I've gone to the specification, I've gone to the annex where it gives us the Little Man computer instruction set, and I've got the information from it there. It says on the right hand side of that column, you can see the alternative mnemonics are accepted, okay? But try and stick to the mnemonics that we've been using, and because that's what they're using in the exam question. So here, what I'm going to do is I'm going to draw exactly what we did before. Yes, it's our boxes again. We've got an accumulator. We've got an arg1. So I imagine that's argument 1. arg1. We've got an argument 2. arg2. I'm just looking down here. Argument 1, argument 2. We've got loop. Loop looks like a label to me. And we've got argument 2. I've already got that. I've got out as well. There's no values for argument 1 and argument 2 in dat yet, because sometimes you might see a little 0 here, but I need an output as well, so I can output something. I'm thinking they're all the boxes I need, to be honest. So let's start at the top. I don't know what it does, but it tells me what the inputs. I'm going to input 13 followed by 5 after that. So when I put input, that's going to be the value of 13. It says store, so 13 goes into the accumulator. Store argument 1. So we store the contents of the accumulator in argument 1. Done that, done that. Input the second number, which is 5. So 13 gets scrubbed, 5 goes in. Done that. Store that value from the accumulator in argument 2. 5 goes in there. No problemo, easy peasy. Then it says load argument 1. Okay, no problem. Load 13 from there. Overwrite 13 is now in the accumulator. Happy days. Then it says subtract argument 2. So I've got 13 there. I'm going to take 5 from it. And what's that going to leave me with? It's going to leave me with 8, isn't it? Yeah, 5 taken away from 13 leaves us with 8. So it says here, I need to scrub that out, put 8 in there. It says branch if positive. Okay, branch if positive. Is that a positive number? Yes. So it says go to loop. So we jump from here back up to loop. And we subtract argument 2 again. So we take 5 from 8. What does that leave us with? Leaves us with 3. Okay, strange, but there we are. Subtract, so we've done that, and now we go branch if positive. Well, 3 is still positive, so we jump back up to loop, and it says, okay, right. So we take 5 again from this. What does that leave us with? -2 this time. Done that. Branch if positive. Well, no, because the contents of the accumulator is -2. That's not positive anymore. So I would skip on and move sequentially down the order. Then it says add argument 2. So I add argument 2 to this. So I add 5 to -2, which those eagle-eyed mathematicians amongst me would say, okay, it's 3 then, isn't it? Then we output that. Okay, we output the contents of the accumulator, which is 3. And are we done? No halt command, but we're done, aren't we? So that's 1 mark, that question, for following that through. It's not too difficult if you're using your box method. And there we go. There's the answer. It outputs 3. Not bad, not bad. Now what about this question? State what it does. Well, if I just flick back for a second, what did it do for us before? Try and have a look at that. By all means, pause the video. But look what it did. I started off with 13. a -5 from it, a -5 from it again, a -5 from it again, and then it returned a -2. What do you think it does? Now, think about it like this. We started off with 13 and we kept taking 5 out of it. And what that does is that creates the division. Let me just skip on. So remember that we started off with 13 and we minused 5 from that. And that gave us 8 left over. And that was our first whole division. Then we had 8 and we minus 5 from it again. And that gave us 3 overall. And that was our second whole division. After that, we then looked at the next one, which was 3, and we minus 5 from that, and that gave us -2. And then the program actually added 5 to that, which gave us 3 overall. So if you think about it, we got 2 whole divisions here, and we've got a remainder from the division, because we can't divide it because it doesn't go into 5 properly. This is our remainder. So what this algorithm was actually performing was a modulus operation. So if you did 13 mod 5, you'd get 2 whole divisions and 3 as a remainder. And this is what we keep in a modular division. So I think now it's time to look at a different kind of question in there. There's the answer if you needed it. We've got a bit of a scenario going on, but a big chunk of assembly language. So a digital coffee making machine has a CPU that uses little man computer instruction sets. Part of the coffee making machine code asks the user to press a button to select its strength. The code outputs 1, which will switch on a green light to indicate the valid selection, or it outputs 0 to indicate an invalid selection. The code is shown below. So we've got a series of assembly language, code commands, we've got labels, we've got inputs and data and all sorts going on in there. It says tick the appropriate boxes below to indicate which inputs will result in a green light, i.e. the code outputs 1, or a red light, i.e. which the code outputs 0. It's only worth 2 marks, so it can't take us very long, can it? Surely. And what we're going to do is start off by doing the box method again. So I'm going to work out first. I've got an accumulator. I'll write that in here. ACC. I've got an output, or I will have, hopefully. And I've got STA entry, so I'm looking down at the bottom here. I've got green light, red light, max, and entry. Wait, let's have a look. Yeah, green light, red light, max, entry. Yeah, that's right. So green light, red light. I don't know why I'm writing it slanted. Green, red is 0, green is 1 according to this DAT down here, and we've got max as well, which is 5, and there's no recorded value for entry. Oh, I have no idea why I'm slanting that much. Anyway, so let's start off then. We've got our inputs on this left hand side. We've got to fill the table in. The first input is 1. So I put 1 in there, and we store that value in the accumulator, and we store it in entry. So 1 gets stored in entry. Then it says LDA max. So we load max, get rid of that, load max into the accumulator, and then it says sub entry. So we take 1 from 5, that gives us 4, and then it says BRP accept. So branch if positive. Is it positive? Well, 4 is positive, so jump to accept. So we jump to accept, which is here, and it says LDA green light, load green light, which is 1. And what does it say do then? Out. Okay, so we output green light. So we tick this one. Green light. Do we stop? Out, halt. Yes, we do. We stop. Okay, excellent. Done that one. Now we start again and we do number 2. So number 2, input. This is going to get messy in this box. Apologies in advance. Input 2. Store that in entry. Entry, store in entry. Load max. Max goes in, max is 5. Sub entry, take away 2 from that, that gives us 3. Sub entry, branch if positive, yeah, it's positive, go to accept, green light, no problem. 3, let's go for input now, input 3, store it in entry, go over to entry. I should have put 1s in here, cross that out, cross that out. 3's gone in there, yep. Load max, there you go, 5 gets loaded. We subtract the entry, so we take 3 from that, that gives us 2 left over. And then branch if positive, well, it is positive still, so accept. And if you're an algorithmic person looking at pattern recognition here, you can probably see where this is going, but I'll go through the process just to show you anyway. Okay, so branch if positive, accept, we load the green light gets loaded, and then we output. I would put 1s in here, but you get the point. Once the green light gets loaded into the accumulator, we output it. So we've had 3 green lights so far, and we keep going. Okay, so input 4, STA entry, 4 goes in entry, we load max again, load max. I'm going to subtract the entry, which is 4 taken from 5, that gives me 1 left over. Is it positive? Yes, it is. Jump to the accept and load the green light. Yep, load the green light. Wonderful. And then we move on. So the next entry will be 5 this time. We input 5. We store the entry. We store 5 in there. We load the max, which is 5. So 5's already in there, so I won't rewrite it. I'll leave it as it is. 5 minus 5. Okay, 5 take 5 is 0. So that ends up in 0. And then we do branch if positive. Now, branch if positive or 0, we're going to accept that. So that also gets a tick in the box because we jump to accept and we load the green light again. Now, I imagine this is where things start to change. So this time, I'm going to put in 6 because we input 6, and we're going to store that in entry. So off we go. 6 gets stored. Then we're going to load max. So we load 5. And then it says subtract the entry. So the entry is 6, and we're going to take that away from 5. That gives us minus 1. Minus 1. So branch if positive or 0, that fails. So we failed at this line now, so we move sequentially to our next one. It says load red light. So you'd load 0 into the accumulator, and then you would branch always. So you're going to branch no matter what. It jumps us to print and end. So we jump to this line, print and end, output and halt. So we output 0 this time. 0 gets outputted, and that means we're going to have a red light. Okay? Now, you could probably see that as we carry on, they're always going to result in negative values, so they're probably going to be red lights. Okay, so 1 to 5, they're the first 5 accepted selections. After that, they are not valid selections at all. Let's have a look if we were correct or not. So we've got 1, 2, 3, 4. We've got 5 ticks in green and 4 ticks in red. 5 ticks in green, 4 ticks in red. Were we right? Rows 1 to 4, correct, 1 mark. Well, we got all of those. Rows 5 to 9, correct. So that was green as well, so we got that. And we got 4 red ones. So well done to us, 2 marks in the bag. You can speed up how quickly you answer that question if you spot the patterns as you go. So that concludes our assembly language programming video. In the next one, part 3, I'll cover a strictly A2 topic, and that is memory addressing. So do join me for that one, where we go a little bit deeper into how things are passed around in the memory side of this process. I'll see you soon.